If developers avoid your doc site and search the web instead, internal search is failing. We will build a small hybrid BM25 plus embedding setup that makes documentation search usable again. You see users typing natural queries and getting irrelevant pages. You want a search that finds the right endpoint or example, not just any page that shares a word. By the end, you will understand a lightweight pipeline that combines keyword precision with vector similarity, so your docs return useful pages first. This is practical, incremental, and testable. I'm Professor Pi, teaching search and IR from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Start from the problem. API documentation is messy. Pages repeat terms. Users ask for intents, not exact words. Plain keyword search surfaces pages with the most overlapping words, which often misses the right example or parameter. BM25 gives a better keyword signal by downweighting common words. Embeddings capture conceptual similarity, so a page that explains rate limiting can match a query about throttling, even if the exact word differs. Hybrid ranking mixes both and gives a fast, robust baseline for internal doc search. Conceptually, think of BM25 as a smart keyword counter. It rewards rare query words more than common ones. Embeddings act like meaning fingerprints. They score documents by how conceptually close they are to the query. BM25 keeps precision when users ask for a named parameter. Embeddings find the right concept when users use different wording. Each has weaknesses. BM25 can miss synonyms. Embeddings can drift to loosely related pages. Together, they balance precision and recall. We will build a toy pipeline that uses a tiny in-memory corpus, computes a simple BM25-like IDF signal, ranks by weighted keyword matches, computes a binary embedding-style cosine over token sets, and then blends the two signals for a hybrid top result. This keeps the code compact and the ideas clear before you scale to real indexes or learned embeddings. Now we seed a tiny corpus and run a baseline keyword winner. This snippet seeds toy API docs and returns the keyword match winner. We create a tiny in-memory corpus called docs with short endpoint-like strings and a simple query queue. The set QT holds query terms so we can count overlaps without double counting. The max call scans each ID and text pair and sums how many query words appear in the document text split by spaces. The document ID with the highest overlap is selected as top, acting as a fast baseline keyword search. The printed ID shows which page a plain keyword pass would surface first and why it matters for relevance. Next, we add a measure of rarity to words. This snippet computes an IDF signal to weigh rare terms higher. We build a vocabulary from docs and count in how many documents each token appears in the mapping DF. Using N as the total docs, we apply a BM25-style IDF formula to the token limit to estimate how distinctive it is. A larger IDF means the term appears in fewer documents and should get more weight in ranking. If the corpus grows or a word spreads across many pages, its IDF falls and it becomes less influential. The printed value quantifies how informative the word limit is for our corpus. Now we use those IDF weights to sort pages. This snippet ranks documents using BM25-style IDF weights. We first compute document frequencies only for the query's terms and convert them into IDF weights, so rare query terms matter more. For each document, we sum the IDF of any query token present in its text as a compact BM25-like score. The sorted list SC orders documents from most to least relevant according to these weights. If you add more overlapping but common terms, scores rise slowly. Rare terms push scores faster. The printed top 2 shows how weighted keyword ranking changes the ordering compared to plain overlap. Next, we add a simple, vectorish signal using token sets. This snippet scores with a simple embedding-style cosine on token sets. We treat each document and the query as vectors of unique words and use binary cosine similarity for a fast semantic-ish signal. The variable QS holds the query set, and each doc gets normalized by its set size, so longer texts aren't unfairly favored. The sorted list, SC, ranks docs by their cosine scores, highlighting conceptual overlap beyond raw counts. Increasing query breadth adds tokens and can slightly dilute similarity. Trimming to core intent sharpens the score. The printed ID and score show the top vector similar document and its score. Finally, we blend both signals for a hybrid result. This snippet blends BM25-like and embedding signals for hybrid re-ranking. We estimate inverse frequency in IDF and build a BM map that rewards documents matching distinctive query terms. In parallel, M computes binary cosine similarity to capture semantic overlap between token sets. The final top ID maximizes a weighted sum, 0.6 times BM plus 0.4 times EM, balancing keyword precision with concept similarity. Increase 0.6 to favor exact term matches and reduce semantic drift. Decrease it to retrieve conceptually similar but not exact matches faster. The printed ID shows the hybrid winner, a practical baseline result. This toy pipeline maps cleanly to a real system by replacing the in-memory corpus with your documentation store, swapping binary token vectors for dense embeddings, and substituting simple IDF with a production BM25 implementation. Recap. Hybrid ranking combines BM25-style keyword weight with a vector similarity signal. Use it when docs need both exact term precision and concept matching. Caveat: the blend needs careful balancing, or you will favor one signal and lose the other. Next step, tune the BM25 weight and the blend coefficient. For example, adjust BM25 K1 and B while testing changes to the 0.6 versus 0.4 hybrid weight to find the best mix for your corpus. If short, practical IR helps your docs, subscribe and watch the IR videos.